Hi everyone, this is Ihab Mohammed. Today I will present our proposed log-MPPI controller strategy for autonomous navigation. The main objective of our work is to perform autonomous navigation in unknown cluttered environments such as forests, underground mines, warehouses, as you can see in those videos. So from the control point of view, our goal is to find the control sequence that generates a collision-free trajectory, which allows the robot to navigate from point A to point B while minimizing a predefined cost function. To do so, the robot should be able to perceive its surrounding environment, then react properly. This indeed results in a very complex optimization problem that is difficult to be solved in real time. One of the promising control strategies is MPPI, which is a sampling-based empathy method that can be applied to nonlinear dynamics and the non-convex cost function. The key idea of MPPI is to sample thousands of trajectories in a real time from the system dynamics. Then, each trajectory is evaluated according to a predefined cost function. To achieve a real-time performance, all trajectories are executed in parallel using a GPU. After that, the optimal control sequence is updated over all trajectories, as you can see in this figure. This optimal control sequence can be updated using this equation, where the cost to go of each trajectory equals the terminal cost and the running cost, while this running cost is equivalent to the state dependence and the quadratic control cost, where nu refers to the exploration noise, which actually defines how aggressively the state space is explored. M and N refer to the number of trajectories within a time horizon n, while delta U is a zero mean Gaussian noise, represents the control input updates. We can clearly see that this control law is a derivative free, and there is no need for the derivative information to find the optimal solution. In spite of the attractive features of MPPI, it might produce an invisible trajectory when the distributions of all trajectories are located within high-cost regions. One solution could be adjusting U and sigma. However, if nu is too large, the controller produces control inputs with significant chatter. Also, a higher value of sigma might result in violating the system constraints. Instead, in this work, we inject the log normal along with the normal distribution. In other words, the control input updates is defined as the product of the normal and the log normal distributions. With such a sampling method, we ensure much better state exploration and reduce the risk of getting stuck in local minima, leading the robot to find the visible trajectory that avoid collision. We also present a method for collision-free navigation in a known environment by directly integrating the 2D occupancy grid as a local cost map into the optimization problem of MPPI without adding additional complexity to the optimization problem. With the aim of demonstrating the potential advantages of our proposed control strategy, we conduct intensive simulation considering 4 scenarios. In the first scenario, the intensive simulations are carried out considering different values of lambda and sigma, with the aim of choosing the best set of values that respect the control constraints. Then we randomly generate 3 different types of forest. Each type has 50 different maps. In the first type, the obstacles were 1.5 meter apart. The second was 2 meters apart, while the third one was 3 meters apart. The obtained results demonstrate that log-MPPI has more flexible trajectories than the classical MPPI, resulting in reducing the probability of getting stuck in local minima and improving the quality of the generated trajectory towards the goal. Please keep in mind that in all simulations we ensure much better state exploration with more than 30% reduction in the injected noise variance when MPPI is used. This video shows the performance of both control strategies in an unknown forest-like environment with a density of 0.2 trees per meter square based on the 2D local cost map built by the robot on-board sensor. Here the maximum desired velocity of the robot is set to 1.5 meter per second. We can notice that the log-MPPI outperforms MPPI and there is no collision, and the average trajectory length is about 4.3 meters shorter than that for MPPI. Here we show the 2D grid-based navigation of our proposed method in the dynamic environment. The simulation results demonstrate that the autonomous vehicle successfully avoids the moving agents. However, we noticed that the more the deployed agents, the noisier the 2D cost map, increasing the risk of being trapped in local minima. Finally, we experimentally validate the applicability of the proposed control strategies for achieving a 2D grid-based collision-free navigation in an unknown indoor cluttered environment. Both control strategies provide a real-time collision-free navigation in the given environment. However, our approach again outperforms the classical one. Please scan the QR code for watching the entire real-time and simulation results. Also, please feel free to shoot me an email if you have any doubts or looking for collaboration. Thank you so much for watching.